General relativity, step by step. I was considering the closed universe solution, which had this thing here as a line element for an instant in space, where chi was r over r0, so sort of non-dimensionalized r. I'm going to look at the other term now. So we've got ds squared equals r0 d chi squared plus r0 squared sine squared chi d phi squared. And we're going to consider the same result. Why am I doing this? I'm doing this because, if we go back a little bit, before I was looking at this with the sine squared solution here. Now I'm looking at the first solution with a positive k for the constant of integration. So q is equal to r0 sine r over r0. So again, it's a non-flat space. And we can go through the same business here. We can get a circle and we can go around it, and the circumference comes out to be 2 pi r plus, instead of here we had minus, it's going to be plus some stuff. So the circumference is strictly greater than 2 pi r. So that distance there is r, and the circumference is greater than 2 pi r. Again, a feature of it being a non-flat space. It's a little bit harder to draw this one, but I'm going to try here. What we're considering is a negative curvature space. It sort of looks a bit like this. It's a bit difficult to draw. It sort of goes round there and then goes. We're considering it's curving round this way in one direction and the other way in the other direction. So when we consider a path round it at constant r, the circumference is sort of a wiggly wobbly line. It's a bit like a Pringle. Yeah, it's very like a Pringle potato chip. And it's pretty obvious geometrically that the circumference is greater than 2 pi r. Let's see if I can find a Pringle chip and see if I can Google a Pringle. Don't seem to be able to control my interface very well. Never mind, let's try again. Come on. Oh, it's this one. Pringle chip. Let's have a look at that. Oh yeah, here we go. There's a nice little picture of a Pringle chip. You can see it's got curvature in this sense in one direction and in the opposite sense in the other. And so the circumference is larger than 2 pi r because it's got this peculiar curvature structure. But again, I want to be clear that this picture here is no illustration, it's no indication of the global topology of the universe. The local curvature could be like this one here, could be like this picture here, and yet the global topology still might be that of a torus, because we do not have the requirement that we have to embed our space into a large dimensional superspace. So I'm going to stop there. Actually, I'm not going to stop there. I'm going to carry on talking for just a little bit. In all of this here, we're considering just a single instant in time. And I guess this is leaving open, or I haven't really started to think yet about, I'm just flicking backwards through here. I was more interested in the curvature of the spatial component. I've been ignoring this A of t term, the Hubble expansion term there. And of course, this is where general relativity becomes quite interesting, because what we're going to have to do here is to find dynamical equations which solve for A of t. And that's going to require a lot more physics than we've used before. We're going to need equations of state, we're going to need physics of photon gases, we're going to need to know something about the large-scale composition of the universe, and it's not at all easy. But we're going to have to try, and I'm going to do that in the next screencast, so I'm going to stop there. Stop!